Somebody was here and they went, they left. I guess they got tired of waiting.
Again, you need to be able to quote the chart. So let's say you make a 90% on the identification, and then you make a 60% on the rote memory questions. 90 plus 60 is 150. 150 divided by 2 is 75. So that would be your grade on the practical. So the identification and the muscle chart questions count equally. You will have roughly on exam 3 about 25 muscle chart questions. On the final, 25 muscle chart questions.
And now you probably know how many points everything is worth, but just in case you want a visual.
So exam 3 is worth 100 points. So you're going to have, maybe, this is going to work out to 25 to 35 points. And the final is worth 200 points. If you've got 25 muscle chart questions there, it's going to work out to around 50 points. And then the muscle practical, 50% of the grade. And the muscle practical is worth 100 points. So that's another 50 points. So we've got 50, 100, 125 or so. So around 125 of those 1,000 points come from the rote memory of the muscle chart. People, that's a letter grade. I've said this before. I see C's fall to F's. I see A's fall to B's. Don't let that be you. It's no fun memorizing the muscle chart, but it is simple. It is so easy. We've talked about this before. We talked about this day one. Anatomy and physiology. Translation, rote memory and understanding. Go back to this picture and you saw this, you studied this in Psych 101 and don't care where you took it. These are the different levels of cognition. The bottom, recall, that's rote memory. A dog can memorize 200 words. You're a lot more intelligent than a dog. Physiology is all the stuff above knowledge or recall. So the muscle chart is not difficult, it's just boring. And because it's boring, we don't like doing it. We prefer to understand things, and that's just because we are intelligent creatures. But I guess you kind of have to just bite your tongue and do it. Please don't destroy your grade. I mean, you're still here. All the time you've put into this class. Also use the muscle chart to raise your grade. You're teetering between a C and a B. Maybe your average is 78, 79%. Facing the muscle chart could be with that thing you need to take you over the edge. But again, you need to be able to quote it. A vague recollection of it won't do it. Okay, I'm going to show you the format that I use for the muscle chart questions because I don't want any surprises. So these examples come from old quizzes. This first example is the way the muscle chart questions work in this room. Okay, so exam 3 and the final. So you'll have 4 or 5 of these blocks of 5. So 5, 10, 15, 20. If there was another block, it'd be 25. You've got muscles on the left and something on the right. This might be action, it might be insertion, it might be origin, it might be antagonist. Every letter over here gets used. No letter gets used twice. And this A through E goes with this 1 through 5. This A through E goes with this 1 through 5. A lot of people actually love these and find them simple because they've memorized the muscle chart. The format in the lab is a little more difficult. It's different, but it's also a little more difficult. So the first thing you'll notice about the format in the lab is that for every 5 muscles on the left, you have 6 choices on the right. So there'll be something over here that doesn't get used. The other thing you'll notice is that this block doesn't necessarily go with this block. This block doesn't necessarily go with that block. So these are shoulder muscles, scapula muscles. Look, those are things in the leg. These are things in the arm, the wrist. These are muscles in the leg. So the first thing you'll do when you're given this is you'll say, okay, I think this goes there. This looks like it goes there. And this one goes up there. And then you'll know which block on the left goes with which block on the right. Then you'll proceed to match them. And again, they're little puzzles. You can quote the muscle chart. It'll be simple. 3 points. Our questions on muscle chart questions. How they work, how valuable it is. Let's remember, we've known this since the semester started. This is the syllabus, which you were given before the semester started. And right here, I even tell you that I suggest you start memorizing the muscles immediately. Some of you have because we talk, but we text over the weekend. Please don't put this off. Okay, here we go, muscles. So a lot of these study tips, letters A through H, came from Shanna or Krista. Most of them did. And you know, there it says again, be absolutely sure you memorize the muscle. I recommend you make a flashcard for every muscle. Put the name of the muscle on the front and the information in the chart on the back. So you've got simply name on the front, on the back, origin, insertion, action. Use them with a friend. Use them with your brother. Use them with your father, your Uncle Frank. If They show you the name of the muscle, you should be able to regurgitate the origin, insertion, and action. Or flip it around. Let them show you the origin, insertion, and action, and you name the muscle. If you're 21 years old, do it with shots of Tito's. You miss it, you take a shot. You get it right, you don't have to take a shot. Now, what's going to happen if you miss the first one and you miss the second one? Pretty soon. I'm kidding, I think, but I've seen it all, man. I've seen it all. I've seen students convert a Monopoly game to the muscle chart, and they sit and they play it for hours. A group of 4 or 5 people. Meg, Sarah, Stephanie, Johnny, Dan. I think there was another one. But they'd sit for hours. They were doing this during the pandemic. They were doing it via Teams. And then when we came back to campus, well, we were never really off campus, but we were all isolated. You know, you weren't supposed to go visit people. But they'd sit in the lab and they'd do it. And anything you can do to make it more fun, less, you know, the hardest way in the world to do it is to sit by yourself and memorize it. Do it with somebody. It'll just be more fun. It'll be easier. Shanna said, watch the videos again. You've watched the videos in context of the bones, but watch them again, because now that you're memorizing origins and insertions, when you see some of these bumps on the bones, like when Larry shows you the mastoid process of the temporal bone, and in the muscle chart, you're learning that that's the insertion of the sternocleidomastoid muscle. The videos, you might get things out of the videos that you didn't get before. Shanna said, Larry, you know, you always tell them, meaning me, I tell you to use the chart, it goes head to toe. Memorize them in order. That's what I always said. And hopefully, you know, you've all looked at the chart, because I've asked you repeatedly ad nauseum to go through the chart and see if you can find something in the name of the muscle to negate some rote memory. So we start out here with the TMJ. We have chewing muscles, and we have muscles of facial expression. And at the other end of the chart, we're acting on the ankle. So the chart's already organized head to toe. And I always told people, do it that way. Shanna said, well, Larry, wait a minute. What might work better for some people? Why do I keep losing the mouse? What might work better for some people is to start with muscles that they're familiar with. So, you know, chances are people have heard of the biceps. A lot of people have heard of the quadriceps. They don't necessarily know what they are or even where they are, but it's a word they've heard. She didn't list it here, but you could add hamstrings. So maybe that will work better for you. Start with a group that you're familiar with. It could be the muscles that you use to smile, or the muscles that you use to chew, whatever group you want to start with. Use all of your resources. You've got maybe a textbook, maybe not, but you've certainly got a lab manual and an atlas, and they have pictures of these things. I know it seems like an overwhelming task, but you've got to maintain perspective. There are over 600 muscles in the body, over 400 in any elementary A&P book. Elementary A&P book. That's what this class is. It's elementary. I'm asking you to learn about 70 people. We can add a couple of hundred more if you want. You look pissed off. Because of you, I'm going to add 200 muscles. Everybody, there you go. Throw shit at her. Obviously, I'm kidding, but you've got to keep this in perspective. You've got to. It's no big deal. Letter E, exactly what to memorize. Well, the freaking chart, the whole thing, be able to quote it. Organized by regions. It's already organized by regions. It goes head to toe. So you've got the TMJ, the neck, the shoulder, the chest, the back, the hips, the knees. G I came up with, and I think it's a powerful, powerful tool. So organized by joints and movement at joints. So again, you would go head to toe. But let me give you two examples, and one's one extreme, another one's the other extreme. So if you were looking at something like the elbow or the knee, there's not much you can do with the elbow or the knee. You can flex the elbow or the knee, or you can extend it. That's it. So looking at the muscle chart, what muscles will flex the elbow? Write them down. What muscles will extend the elbow? Write them down. Okay, so that's one extreme because there's not much you can do with either one of those joints. But on the other hand, if you were working with the shoulder or the hip, my God, so you can flex the shoulder and the hip. You can extend them, flexion, extension, hyperextension. But you can ab and adduct. You can medially rotate, laterally rotate. So using the muscle chart, you would write down the muscles that will do these different actions. I don't see this as creating another document that you have to memorize. I see this as an activity that if you do it, learning will occur. It's just like when you were in high school and you were given homework. The only difference is that in an upper level science class, I don't give you homework. You have to do your own homework, and there's lots of homework. It's just not here as a sheet of paper. You do it and you give it back to me. So this would be homework. And by doing this, learning will occur. You will retain a lot of it. I wouldn't do it at the computer. I would write it out by hand. And maybe it's a set of flashcards. I don't know. But again, just do it and learning will occur. Now, I'm repeating something I just said. I've asked you at least twice in this room, sit down with the muscle chart and ask yourself, go line by line, every muscle, what's in the name of that muscle that will negate some rote memory? I hope you've done that. I'm not going to do it for you. Examples of antagonists, we'll get to that today. Right there. So we'll cover it formally right there. That'll be probably the last thing we do today. For now, examples of antagonists. Antagonist is opposite. So the antagonist of up is down. Antagonist of white is black. Antagonist of 1 is 0. The antagonist of yes is no. So if the action is flex the elbow, what's the opposite action? Extend the elbow. So if the action is flex the elbow, the antagonistic action is extend the elbow. If the biceps brachii flexes the elbow, then an antagonistic muscle is a muscle that extends the elbow. We'll cover that formally here in a bit. All right, so how muscles are named. Again, I'm not going to do it for you. Go. I'm looking for 6, 7, 8 ways. Anybody? If you hadn't done what I asked you to do, do it now. Look at your muscle chart. You need your muscle chart out anyway today. Get it out now. Give me some ways muscles are named. Okay, so would it be fair to say attachments?
Yes.
So they are attached. See, what will happen is if you get something out of the name, you might be able to get something else from that. So, look at, look at, oh, I highlighted chart. Oh, maybe that'll. Okay, so look at those two. So medial and lateral pterygoid. So you're going to associate them with the pterygoid processes of the sphenoid bone. Limited information, but they certainly don't flex the elbow. Sternocleidomastoid. Now this one's awesome. So we get, in fact, I think I've shown you this one previously when I was asking you to do this. So we get sternum, clavicle, and mastoid process. So that means the muscles are attached right here where the sternum and clavicle come together. That's the sternoclavicular joint. And they're attached back here at the mastoid processes. When you contract those muscles, there's really only two things that can happen. If you contract them both, you'll flex your head. So you don't have to memorize that. You can just figure it out based on the attachments. And if you contract just one of them, you'll rotate your head. So all of that in the name. A lot of times you'll see little bony parts, some part that you learned for the practical. Oh, like this one. Attaches to the coracoid process of the scapula. So again, I don't know where you are. I know there are people that email me every single weekend, sometimes all hours of the night, and it's muscle chart stuff, and I commend you. But I don't know where you are personally. You've done nothing else. The first thing you need to do is sit down with the chart, line by line. What's in the name? Is there something in the name that will negate some rote memory? So we've got attachments. What else do we have? I'm looking at one right here on the screen. Mallory, what do you see under coracobrachialis? No, the muscle under coracobrachialis. What muscle do you see? Just read it off the chart. The deltoid. What Greek word comes to mind? What shape is that word? Somebody help Mallory. Delta, the Greek letter delta is a triangle. So that muscle is shaped like a triangle. How does that help me? Well, check this out. Look at its attachments. So it's shaped like this. Look, it's attached to the clavicle and the scapula. So if the muscle sits here, it can be attached anteriorly to the clavicle, posteriorly to the scapula, and then on the side, it's attached to the humerus. And that's how it can flex the arm, extend the arm, and abduct the arm. So simply by the word deltoid, we can infer all of that. Now, yes, there are lots of little bits and pieces there you still have to hold on to. But just the word delta now brings a lot of it to the tip of your tongue. This is how you do it. This is how it's done. One muscle at a time. Mallory, I wasn't picking on you. I thought you would see it and recognize the Greek letter. So anyway, good job, because with a little help, two of you together did it. So good job. So shape.
Is there anything else here that you see a shape in the word? Trapezius. What else did I hear? Rhomboids. Okay. All right. Give me another way that muscles are named. Yeah, go ahead. Excellent. The action. Okay, where's my crystal clear example for that one? There it is. The levator scapula. I bet it flexes the ankle. I guarantee you it elevates the scapula. It's got to. If it elevates the scapula, doesn't it have to be attached to the scapula? So there's a lot in the name. And look at that. Insertion, superior angle of the scapula. All right, give me one or two more, and then I'm going to leave it with you because I'm not doing it for you. Flexor and extensor. Well, those are actions, though. So I want one or two ways they're named. One or two more ways.
Region.
Okay, so region.
No, you got here.
So that's why I went right here. So location or region. I mean the external abdominal oblique, the rectus abdominis. Those are probably muscles in the butt, right? That doesn't make sense. That's dumb. They've got to be right here. And I bet the external abdominal oblique is superficial to the internal abdominal oblique. So we could call that relative location. And from this set we're looking at, we even get the direction of the fibers. The transverse abdominis, they run transversely. They hold the gut in. The obliques, they run diagonally, and rectus means parallel. So the rectus abdominis fibers are right here running parallel. Those are what people call the six-pack muscles. So please use this method. You use the textbook, lab manual, internet, and you'll find 6, 7, or 8 ways muscles are named. And then go down that chart line by line. Try to find one or two things in each muscle that negate a little rote memory. I've shown you this example before, but as we leave this, look at the last two muscles in the chart. I guarantee you they're associated with the tibia. I guarantee you the tibialis anterior is anterior and the tibialis posterior is posterior. So we've got location, we've got relative location. All right, I can't show these two. Well, yeah, maybe I can. So look at Roman numeral 3. It says functions of muscle tissue. Roman numeral 4, types of muscle tissue and histology. So I'm combining those. For the most part in AMP1, when we talk about muscles, we're talking about skeletal muscle. And while in general, when we think about skeletal muscle, we think about moving, walking, running, swinging a golf club, a tennis racket, whatever, a baseball club. What do you call it? A baseball bat, a baseball club. But well, I guess that's what I was thinking. A defensive weapon.
Yeah.
But can you think of things that skeletal muscles do other than movement? Am I using my skeletal muscles now? What am I using them for? Posture, support. So write these things down. Number one, movement. Number two, posture, support. But I want to go beyond all of that. Because again, when we think about muscles in AMP1, we're for the most part thinking about skeletal muscle. Smooth muscle, cardiac muscle, that's more of an AMP2 topic. So we're thinking about skeletal muscle this semester. And when we think about skeletal muscle, we primarily think about movement. But what else do you use skeletal muscle for? Am I using it right now? 1, 2, 3, 4, 5. Speech? Yeah, talking, speech production. Do you have any muscles on your muscle chart that have anything to do with breathing? Diaphragm, the internal and external intercostals. So breathing, kind of an important function. Have you ever pooped? You use your skeletal muscle when you poop. The technical term is defecation. Anybody know anybody that's had a baby? Use your skeletal muscle when you have a baby. Okay, so see, there are lots of things that go beyond dancing and walking, things that go beyond movement. So don't forget those things. Now, and again, we're combining Roman numerals 3 and 4. 3, as you can see, is more on functions. 4 is more on histology. And we will, here in a few minutes, we'll actually look at the muscle pictures that you have in your histology book. But as we think about skeletal muscle and its histology, skeletal muscle cells are huge. Very large cells. Now in biology, middle school, high school, biology 111 here or in North Carolina, wherever you took it, when you started talking about cells, one of the things at the very front of the chapter was, why are cells small? And there are several reasons why cells are small, but one reason cells are small is that a single nucleus can only control a certain amount of area. It's kind of like a business. I mean, the people at Walmart that work the cash registers, they don't report to the CEO, do they? Think about all the levels of management between the CEO and the people that work the cash registers. So how do muscle cells get around this problem of cells need to be small because one nucleus, one manager, can only control so much? Skeletal muscle cells are multinucleated. You've got number one, they're huge cells. Number two, they're multinucleated. So see, in biology, what you would have done is say, this sheet of tissue can't be controlled by one nucleus. It's too big. So it's divided up into many cells, and each cell has a nucleus. Just like the organization of a corporation, from the people that dig the ditches up to the CEO. Well, the way skeletal muscle cells fix the problem is that one giant cell has many nuclei. So you've got number one, huge cells. Number two, multinucleated. We'll go to a diagram begin with. So this is and we'll look at just the diagram first. This is a cell. This is the cell membrane. Sarcolemma means cell membrane. Look at all the nuclei in that cell, multinucleated. So we've got large cells, multinucleated. Now what about shape? What is the shape of that thing? Cylinder. They're cylindrically shaped. So that's number 3. Large cells, multinucleated, cylindrically shaped. Above that diagram is a photomicrograph. We don't really get the cylinder aspect in the picture, but we do see multinuclei. Now, what could you say about the location? We'll go back to the diagram because it shows us the cross-sectional end on the left. What could you say about the location of the nuclei? Because in biology, you always start with, there's a cell, people. There's its brain. It's called the nucleus. It's kind of like your brain. It controls the cell. Do you see any of these nuclei in the middle? No. So where are they? They are blank located. The nuclei are peripherally located. So we've got large cells, cylindrically shaped, multinucleated, peripherally located nuclei. One more thing you can look at in this picture. The cell looks like it is striped. Don't write striped. Vertical striations. So you've got large cells, multinucleated, peripherally located nuclei. The cells are cylindrically shaped. They are striated. But guess what? Striations are an illusion. They're not really there. I won't be able to explain that today. I probably will on Wednesday. It might be next Monday. I'm not sure. But for now, the striations are an illusion. We see them here too. We see them in the photomicrograph. I mean, I see them too, just like you. But they're not there. All right, let's go to your histology books. So this is the detailed key. If you've got it with you, you can get it out. If you don't, make a note that we'll be looking at picture number 118, 119, 121, and 123. If you look right now at 19 and 21, you'll see most, if not everything, I just told you about muscles. So we've got movement, posture, ventilation, facial expression. The cells are long, cylindrically shaped, multi-peripherally located nuclei appear striated. Right, in your histology book, and you already have these pictures printed. I told you we would get to them later. So this is the one I like most for skeletal muscle. I see the striations. I can see that the nuclei are peripherally located. Look, if you look there, along there. Multinucleated. See, guys, this is one cell. This is one cell, one cell, one cell. So to get around that problem of cells need to be small because the nucleus can only control so much area by having many nuclei. All right, the next type of muscle is smooth muscle. Smooth muscle is in the walls of hollow organs. It's involuntary. Skeletal muscle is voluntary. Smooth muscle is involuntary. Again, walls of hollow organs. Do you have smooth muscle in your brain? Well, is your brain a hollow organ? I hope not. Brain is a solid organ. You don't have any smooth muscle there. Give me 2 examples of hollow organs. Stomach, small intestines. Those are so connected. Give me one more. Gallbladder, a meniscus, huh? Ureter? Uterus. Yeah, absolutely. Yes, you definitely have smooth muscle in the uterus. Somebody said small intestine. If we go back to a picture that you're extremely familiar with from histology, and as you know, it's my favorite cross-sectional picture of the small intestine. So we had this innermost layer, which is called the mucosa and is made of simple columnar epithelial tissue. Next, we have the submucosa, which is made of lamina propria. That is the muscularis. It's made of smooth muscle. Now, as I've stressed with histology, it serves to introduce many systems of the body. We'll build on this next semester. We'll divide the muscularis into 2 sublayers. You have muscle fibers that run around the small intestine and muscle fibers that run perpendicular to the plane of the board or parallel to the small intestine. But that's something for next semester. And then this outermost layer is the serosa, or visceral peritoneum. And that takes us way back. We're on page 32 of the notes. Get that on page 7. We talked about membranes, visceral and parietal, pericardium, pleura, peritoneum. So that visceral peritoneum called the serosa. We're talking about the intestine. Tie everything together, please. All right, smooth muscle tissue. People will use the phrase spindle-shaped cells. I don't really have a visual when I hear the word spindle. I don't know if you do, but when you see smooth muscle cells just diagrammed, the picture typically looks like this. Spindle-shaped cells. There won't be any striations. They won't be multinucleated. There's nothing about smooth muscle tissue that's like this, you know, kind of cool. A lot of stuff here to talk about. Nothing like that in smooth muscle. And kind of cool looking. Your smooth muscle picture is number 118. Detailed key to histology. Like this. So again, nothing terribly impressive or exciting to look at. The way skeletal muscle is. Right, the one that is really the most interesting is cardiac muscle tissue. The only place in your body you have cardiac muscle tissue is in your heart. Where else? Okay, so it's not in your blood vessels. Be clear, it's in the heart, nowhere else. If we look at the wall of the heart, there's a very thin inner layer. It's actually an epithelial tissue, very, very smooth epithelial tissue. There's a very thin outer layer, and everything in between is the cardiac muscle tissue. This red outer layer is the epicardium. The green inner layer, the endocardium. And it's made of endothelium. Endothelium is a special type of simple squamous. It is the smoothest tissue in the human body. The last thing you want is anything to obstruct blood flow or anything for the blood cells to stick to. So whether we're talking about the lining of the heart or the lining of blood vessels, the lining is a tissue called endothelium. And again, it's a special type of simple squamous. But as you look at that wall, you can see that the bulk of that wall is the myocardium. Now we have the same thing over here. It's just not as pronounced because the right side of the heart is not as strong as the left side of the heart. The left side of the heart is having to send blood to the whole body, okay, the brain, the toes, the fingers, the back, the stomach, the gonads, everywhere. The right side of the heart just has to send the blood to the lungs and back. When those chambers, well, they're called ventricles, but I don't care if you know that right now. When those chambers contract, whoosh, and they eject the blood, each chamber ejects about 75 milliliters. But the left side is so much stronger because it has to send the blood so much further. Anybody have any idea how far it is through all of the blood vessels in the human body? Like if we took all of Mandy's, who I usually call Brandy, yeah, it's like 50,000 miles. If You take all of the blood vessels out of a human and you lay them out on the ground, 50,000 miles. And about 75% of those vessels are the capillaries, because they're the functional part of the vasculature. Just like seeing the alveoli are the functional parts of the lungs. The nephrons are the functional parts of the kidneys. When you think about blood carrying oxygen, when you think about gas exchange occurs at the capillary level. Gases don't move in and out of the big blood vessels you can see in your arm. 50 to 60,000 miles. All right, let's take a look at this photo microscopically, and then I'll talk more about it, because I want you to understand just what an incredibly powerful pump the heart is. It is a pump. I want you to understand how strong, how powerful it is. Cardiac muscle tissue is number 123 in your histology books. And you can read right here what I have to say about it. You don't see striations. What you do see is you see that it's highly branched. So identifying these three types of muscle tissue is very easy. Let's compare it to the vertebrae. What type of vertebra is this? The first thing you ask is, does it have transverse foramen and the transverse processes? If yes, it's cervical. If no, move on. It's either thoracic or lumbar. Then you would look at the spinous processes. Are they long and thin or big and square-like? So with muscle tissue, what type of muscle tissue is this? Is it striated? If yes, it's skeletal. If no, it's either smooth or cardiac. If it is smooth, it won't have anything fancy to look at. If it's cardiac, it will be highly branched. Pretty easy. Skeletal muscle cells have some very specialized cell junctions. A perspective, back to biology again. You talked about cell junctions. I'm sure you recall gap junctions. But cardiac muscle cells have a special type of cell junction called an intercalated disc. These special cell junctions are necessary for two reasons. The heart is such a powerful pump, it could destroy itself, shred itself, tear itself apart, rip the cells away from each other if they weren't held together by these special junctions. The second reason that cardiac muscle cells have these special junctions is to move the electrical signal from cell to cell. Yes, Larry said electrical signal. You all know that there's an electrical signal associated with the heart because you've all heard of an EKG. The EKG is an indirect measurement of the electrical signal moving through the heart. So those intercalated discs are necessary for two reasons: to conduct the electrical signal from cell to cell and to hold the cells together, because the heart is such a strong, powerful pump, it would tear itself apart. Let's spend a minute and look at just how strong the heart is. So everybody has some concept of heart rate. A lot of you can look at your watch and see what your heart rate is right now. A textbook heart rate is about 70 beats in 1 minute. This is at rest. Another value is called the stroke volume, SV, stroke volume. This is the volume of blood ejected every time the heart beats. So looking at this picture again. When the ventricles contract, 75 mils of blood are ejected out of each chamber. So we've got 70 for the stroke volume, or 70 for the heart rate, 75 for the stroke volume. The product of the two numbers is called a cardiac output, CO, cardiac output. Now simplify the expression and you'll have cardiac output. You all know that X divided by X is 1. So I have beats on the top, beats on the bottom. Therefore, cardiac output is volume ejected per minute. So 70 times 75. Now, if you're like me, you cook, you use teaspoons, tablespoons, cups, quarts, pints, not milliliters. So let's once again go back to biology. There's 946 milliliters in a quart. If I divide this by 946, that would give me quarts, and I think we all know there are 4 quarts in a gallon. So if I divide that by 946 and divide it by 4, I can see that the human heart at rest is pumping just slightly less than 1.5 gallons per minute. Now that does or does not impress you, I don't know. But your visual here is the gallon of milk. You're at Safeway or wherever you might shop. King Soopers. Gallon of milk. It's almost 1.5 gallons of milk per minute. Now the heart responds to exercise just like any other muscle does. If you do biceps curls, your biceps get stronger. So if you exercise your heart, say you go out and you swim for an hour, or you walk for an hour, or you run for an hour, or you do the incline, your stroke volume goes up. Let's say that your stroke volume has increased to 85. You'll still have a cardiac output of about 5,250 because that's all you need in 1 minute. So that means your heart rate went down. So 5250 divided by 85. So your heart rate is now 62 beats per minute. Again, this is resting. Some of you have looked at your heart rate. Again, some of you can simply look at your heart and see your heart rate. So if you take up an exercise program, your heart gets stronger, your resting heart rate goes down because the heart becomes a stronger pump. There are two freaks of nature, and I say that with all due respect to these two men. They have resting heart rates of 32. That is because their heart is so strong, it pumps 164 mils, more than double the textbook heart. Many of you have resting heart rates around this number because you exercise. You don't have to be doing anything crazy. You're just not a couch potato. You're not sedentary. This is your stereotypical sedentary American. But people that exercise, they're more along this line. Let's look at what did this work out to in gallons? Let's take an Olympic athlete. And we'll say it's a pretty physically fit person. They have a resting heart rate of 45. Because their heart is a very strong pump. They've got a stroke volume of about 117. And they're running the Olympic marathon for the gold medal. They crank their heart up to 190 beats a minute because they've got to run a 4-minute, 50-second mile uphill, 20 miles into the marathon. They want that gold medal. And they increase their stroke volume by 60%. Because when your brain sends a signal to the heart, making it beat faster, it also makes it beat with more force. So I'm going to increase the 117 by 60%. So now their stroke volume is 187. 187 times 190, 35,568 milliliters per minute. Let's put that in stupid American units. So I'm going to divide it by 946 to get quarts, divide it by 4 to get gallons. You picture 9 of those 1-gallon containers of milk at King Super. The human heart in a trained professional athlete can pump nearly 9.5 gallons of milk, of blood in 1 minute. It is a powerful, powerful pump. We'll do a lot with this particular math in AMP2 in the context of the cardiovascular system. For now, more than anything, it's just to illustrate what a powerful pump the heart is. All right, origin and insertion, I've explained that to you already to facilitate you getting started with the muscle chart, but I'm going to do it again right now officially. So muscles have to be attached on 2 sides of a joint if they're going to move a bone or move bones. And so that's my elbow, if you can't tell. So when I contract my biceps brachii and I flex my arm at the elbow, what's moving the most, my scapula or my radius? Therefore, this is the insertion, this is the origin. So as you're studying this muscle chart, got origins and insertions listed for all of these muscles. The insertion is the point of attachment that moves the most. Let's look at the sternocleidomastoid again. The insertion is the mastoid process. When I contract my sternocleidomastoid muscles, thank you so much. When I contract my sternocleidomastoid muscles, what's moving? My mastoid process or my sternoclavicular joint? That's why the chart tells you the mastoid process is the insertion. Tendon versus an aponeurosis. Now start with histology. Dense, regular connective tissue, tendons and ligaments. Tendons, muscle to bone, ligaments, bone to bone. Picture tendons as cords, just like in my diagram there. I've got the muscle, the biceps brachii, and two tendons connecting the muscle to the bones. An aponeurosis is histologically the same thing, but it's more like a sheet. And like the only aponeurosis that you have in your list of muscles that you have to memorize is right here. The muscle is the tensor fascia latae. And the insertion, which is called the IT band, I don't know if you've heard of iliotibial tract, but I think a lot of you probably have heard of the IT band, especially if you exercise very much. That is an aponeurosis. So it is a set of something that looks like a cord. It's a flat sheet of connective tissue that runs down the side of your leg. And you'll see this in the cadaver. But that muscle, the tensor fascia latae, is not much bigger than my hand. It's right here. Well, how does it insert in the fibula and the tibia? The aponeurosis runs down the side of your leg. Okay, finally, these terms. Prime mover. Now, first of all, these terms are not unique to muscles. They're not unique to anatomy and physiology. Prime mover, for example, is used with the stock market. If they say the Dow went up or down so many points today, the S&P 500 moved so many points today, which stock in that index was primarily responsible? IBM may have gone up through the roof. Apple could have plummeted. Which stock in the index caused the movement? That's the prime mover. So my point there is that these words are not muscle words. They're used all over the place. If you look at a group of muscles that cause a particular action like we have right here, brachialis, biceps brachii, brachioradialis, notice they all flex the elbow. Which is the prime mover? That is, which one is the strongest? Now, when you have muscles like that working together,
One is or rather not one. When you have muscles working together like that, they work together synergistically. And when muscles work together synergistically, it means that the sum is greater than the arithmetic sum. So Mandy, come on down here. See how much weight you can lift. You don't really have to get out of your seat. So she stands right here. Move yourself. God. So let's say that she was able to lift 20 pounds. And I don't know, somebody else comes down. They can lift 21 pounds, and then I do it, and I can lift 22 pounds. So the three of us now are going to do it together. So the arithmetic sum is 63. But because we're working together synergistically, it might be more like 70 pounds. We see this all over the place. If you've got 8 sled dogs, and each sled dog can pull 100 pounds, 8 times 100 is 800. The 8 dogs working together can probably pull 1,000 pounds. If you've got, now we're in the Old West, you've got a horse and buggy. You've got one horse and it can pull 1,000 pounds. So 4 horses should be able to pull 4,000 pounds, but they can probably pull 4,500 because they work together synergistically. Guess how much weight Baxter can pull when he functions as a sled dog? 20 pounds. I'd remember that. Finally, agonist and antagonist. In the interest of time and people out in the hall, we're gonna put that on hold. So Roman numeral 8 characteristics is where we are, except we do have to pick up agonist and antagonist first. Right, if you've got the practical today, I'll see you shortly upstairs. Otherwise, have a nice day, and I'll see you Wednesday.
Write your check this.
Oh, thank you. Okay, because